So here is section 3.3, what derivatives tell us about the shape of a graph. And the first thing is the increasing decreasing test. Suppose f is differentiable on some interval I. If the derivative is positive for all of the values on that interval, all the x values on that interval, then f is increasing on that interval. Now you can probably imagine what it's going to be for b. If the derivative is less than 0 for all x on the interval, then f is decreasing on I. And of course, this has to do with the fact that if the derivative is positive, then you have tangent lines that have positive slope. And if you have a bunch of tangents with a positive slope, that's still going to be creating an increasing function. However, if your tangent lines have a negative slope, at every point, you can see that your function is going to be heading down. So the function would be decreasing. So I'm going to do the proof of one side. It's very similar for the other side. So I'm going to do the proof of A. So we have an interval. So let's let x1 be less than x2. So you have an interval where x2 is just greater than x1. It's going along the x-axis. And these are two numbers, be two numbers on that interval somewhere inside it. So we'll do A. So part A right here for A. We just need to show that as long as x2 is greater than x1, then the same thing is true, that the y value f of x2 is going to be greater than f of x1. So that's just what we need to show. We are given that f is differentiable. Differentiable on the interval, that's given. Suppose f is differentiable. So f is differentiable on that interval given to us. We know that. So we're going to bust out the mean value theorem. So the mean value theorem, I'm going to write MVT, mean value theorem, tells us something. It implies that there is a C, okay, so some number in that interval, x1, x2, such that, or I'll put with, f prime of c equaling that secant line, so the slope of that secant line. So f of x2 minus f of x1 over x2 minus x1. So again, that's the mean value theorem coming into play here. We are given that piece of information due to the mean value theorem. If I were to multiply both sides of that thing that I have there by x2 minus x1, you would see that you're going to have f of x2. I'll just switch the sides on it as well because it's an equation. That is okay. F prime of c times x2 minus x1. So again, multiplying both sides by x2 minus x1, we have that. But since we know that the derivative is positive, and again, that's because that's part of what A is saying, that the derivative is positive on that interval. So we know that f prime of c is greater than 0. And since x2 is greater than x1, we know that x2 minus x1 is also greater than 0. So really all we're saying here is that this piece is positive and this piece is positive. So that means that f of x2 minus f of x1 is also then going to be greater than 0 because that's an equation there. And then that tells us that f of x2, moving the f of x1 to the other side, is greater than f of x1. And by having that, we know that f is increasing. So a similar proof would be used for b if you wanted to show the decreasing part. And it would be just the fact that if x2 is greater than x1, then f of x1 is actually going to be greater than f of x2. So it would be a very similar proof. All right, so now let's use this idea to find the intervals of a function where it's increasing and where it's decreasing. We're also going to find any relative maxima and minima. So the first thing we need to do is take the derivative. So if you want, you can pause and take the derivative and see if you get it right. I'm going to be using the product rule here. Product rule is the easiest way to go. So take a moment, do that, and then come back. So I have the first times the derivative of the second plus the derivative of the first times the second. And of course, because of the plus in between, you can actually have this either way. So the key thing with problems like this is to see that you need to factor. That's the most important thing to then understand. And so notice that I can factor out a 2 and I can factor out an x minus 1. And then I have like a big bracket, which is going to be everything else that's inside. So what I have left from the first piece is an x times x minus 1. And everything that I have left from the second piece is just an x squared minus 6. So that's what I have there. And then what I want to do is combine what I have in those big brackets. The key thing is that what I'd really like to have is everything multiplied together, because that's going to show me all my factors so that I can set it equal to 0, so I can see what factors make this derivative equal to 0, which is of course where we might have some changes in increasing and decreasing. So I have, not that, I have x squared minus x plus x squared minus 6. And I'll put it in now just a softer bracket. Brackets are arbitrary here. And then that's going to give me x squared minus, nope, it's going to give me a 2x squared now that I add them, minus x minus 6. So I have this. And then the goal here would be to see if more factors. If it doesn't, then that factor is going to be irrational in some way. You know, you could use the quadratic formula on that when we set it equal to 0. But let's see if it factors. In factoring this, I'm going to have 2x and x. I could have 6, but that's going to be, the 6 can't be here. If the 6 is here, that's going to be too big for a middle term. And so it's, let's try 3 and 2, but I can't put the 2 over here because, again, common factor is not possible with what I started with. So now I will have, it looks like 4 and 3, which is going to make 1 if this is a minus and this is a plus. Okay. So then the key thing to see here is this derivative is going to be equal to 0 when x is, and then we're looking at all these factors and what makes them 0. So when x is 1, a negative 3/2, and a 2. So all of those things are going to give us a 0 in the derivative. So they're all places where we could change from increasing to decreasing. So now I'll make a little chart here, which has my function, it has the derivative, and of course my x values. And then what I'll do is I'll put those on this, it's essentially a number line. I'm going to put them in order like this. And then I'm just going to see kind of what's happening on either side. So we want to remember that the derivative is 0 at all of these places, and we'll see what's happening on either side. So when we pick something that's less than negative 3/2. So the idea is we're going to put that into the derivative and see if it gives us a positive or a negative value in the derivative. That'll tell us whether the function is increasing or decreasing. So if we put in like a negative 10, because we can put in whatever we want, a negative 10, we're going to see what's happening with the derivative. So if I put in a negative 10, my 2 is never going to change. This first factor is going to be negative, the second factor is going to be negative, and the third factor is going to be negative if I plug in negative 10. So I have positive, which is the 2, times negative, times negative, times negative. That is still negative. And so that tells us that the function is decreasing from negative infinity all the way to negative 3/2. Okay, so we actually already have that piece of information, negative infinity to negative 3/2. Then we pick something between -3/2 and 1. So a common thing would be 0, since that goes from negative to positive. So if we plug in 0, we get positive, negative, positive, negative. So positive times negative times positive times negative is positive. So our derivative is positive in that interval, and that tells us that the function is increasing after that. So we have that interval, -3/2 to 1. And then we just keep checking. So we're going to pick something between 1 and 2. So a value between 1 and 2 typically would be 3/2. If we put that in, we're going to have positive, 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 and then a negative. So positive times positive times positive times negative is a negative. So we're going to be decreasing from 1 to 2. And then if we pick something big like 10, x equals 10, and we plug it into our derivative, we're going to have positive, 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 positive. All those positive multiplied together are still positive, and so that tells us we're going to be increasing after 2. So 2 to infinity, we are increasing. Now we want to think about what the values are at those points. So let's check at -3/2. Let's check at 1. And let's check at 2. So we're going to plug these back in. Understand we're plugging them back into the original function, the f of x, because we want to know what is the y value at those x values, because those points are the local min and max. So if we put in 1, you can see we actually get 0. If you put in 2, you should see that you're going to get, it looks like a -2. And then if you do -3/2, and you can put this into your calculator if you want, or you can just trust me, it is a -23.4375. So we can see here that we've got local minimums with those values where, so understand that the local minimums are coming in when the function goes from decreasing to increasing. So anywhere where it goes decreasing to increasing is going to give you a local minimum. Anywhere where it's going increasing then to decreasing is going to give you a local maximum. So you can see that our maximum is 0 at x equals 1, because we are increasing up to 1 and then we decrease after 1. So that creates a local max. And then we have our 2 local minimums because of the decreasing to increasing, and that's going to be the -23.4375 at x equals -3/2, and we have -2 at x equals 2. Okay, so this is basically what we just saw, which is what's happening when it changes. And so you can see that, not surprisingly, if the derivative changes from, again, this is what we just talked about, if it changes from positive to negative, when the derivative changes like that, at some value, then f has a local max or relative max at c. So again, the derivative is positive, so that means the function's increasing, and then it changes to negative and the function's decreasing, so there's going to be a max up here. And conversely, if it goes from negative to positive at some value, then it has the local min. Now, and that's because, of course, negative means you're decreasing, and then positive means you're increasing, so you have some little min that's down there, some minimum. Now, if the derivative does not change sign, so it does not go from positive to, it might go positive to positive, it might go negative to negative, then it has neither a local max nor a local min, and then we just have to pay attention. All right, so let's take a look at a couple examples. So thinking about x cubed, f of x equals x cubed, find any local minimums or maximums. You might be able to picture this function in your head, and that might help you to kind of think about the fact that, first of all, the derivative, pretty straightforward, 3x squared. And what we know is that if we were to set that derivative equal to 0 and do a whole lot of work, which is not particularly necessary, that we get that x equals 0 is a place where the derivative is 0. So it might make us think, okay, so we have x, we put that value 0, we have our f of x, we have our f prime of x. Fairly straightforward here. If we pick a negative value and put it in the derivative, we do actually get a positive. And if we put a positive value, something greater than 0, into the derivative, we also get a positive. So really doesn't tell us a lot, except for the fact that this function is always increasing. So again, the point here is to see that you might have a place where your derivative is 0, but that doesn't mean you necessarily have a local max or a local min there. You still have to test it to show, in this case, as you can see, that the function is actually always increasing. So for this function, just knowing kind of what we know, I have a slightly different scale on it, so let me fix that a little bit. All right, so we should have -1, -1, 1, 1. These are values on x cubed. So we should just think about that. Like mine's a little bit smushed here. So we have something like this, and then this function comes down, and it goes like this, and you know, it's okay. Doing the best we can with the tablet. So that's what x cubes look like. So it does have a place where the derivative is equal to 0. It's actually just a very, like, one point at 0 where you have a horizontal tangent line, but that's it, and it actually does not change its increasing or decreasing. So in this case, we don't really have to say anything. It's just that it has no local maximums or local minimums, and that's what we test. Okay, one more, and then I'll finish this video. So f of x equals x squared over x squared plus 3. Find any local maxes or mins. So the same question here. If you're given a question like this, the first thing you need to do is take the derivative. This is going to require the quotient rule, so if you want to pause, take the quotient rule, see if you got it right. I'm going to do the quotient rule, and then I'm going to simplify it as much as I can, because I do need to find any values where the derivative is equal to 0. So I have, pause if you want, derivative of the top times the bottom, subtraction for the quotient rule, and then I have the top times the derivative of the bottom. And that's going to give me all over x squared plus 3, and that is squared. And then I just need to simplify as much as I can. 2x cubed plus 6x minus 2x cubed. Oh, how handy and helpful. So now I have x squared plus 3 squared. And then as we can see, not surprisingly, we have some pieces in the top that are gone. And so we have just 6x over x squared plus 3 squared. So the key thing here is local maxes and local mins are when we change from increasing to decreasing, which is what happens on either side of when the derivative is 0. Because we have a rational expression, the only time that this expression can be equal to 0, and this is really key here, the only time that this can be equal to 0 is when the numerator is equal to 0 for a fraction. And so another example of just 0, x equals 0, being our only place where that might happen. So I have x, I'm going to put 0, very similar to the last problem, obviously just a more complicated original function. But then we still just test either side. Notice we're using the derivative here. We want to see what's happening on either side of the derivative. So we're going to pick values that are less than 0, some value that's less than 0, like -5. Notice that when we put values into the derivative, the denominator is something squared. It's always positive. So all we really care about is the numerator. And as you can see, not surprisingly, the numerator just being 6x means that if x is positive, the numerator is positive, and if x is negative, the numerator is negative. So that's pretty helpful because it tells us that if we put in something that is a negative number, that's going to be a negative derivative. And if we put in a positive number, we're going to have a positive derivative. So it tells us that the function is decreasing down to 0, and then after that, it increases. So it does tell us that this function has a local min at, and then because we've learned that when x is 0, we have a local min, we would also want to find f of 0. But as you can see, you'd end up with 0 over 3, which is just 0. So this function has a local min, at local min, let's say a local min of 0 at x equal 0. Okay, and if you would like to know what this function looks like a little bit, we can put some values onto the graph. We already know that we have 0, 0, 0, 0. Notice that because the denominator is x squared plus 3, it's actually never 0, so we don't have any vertical asymptotes here. But do notice that as x gets really, really big, you're basically taking a number and dividing it by that same number plus 3. And that's going to get very, very close to 1. And that's going to happen in either direction. So we end up with a horizontal asymptote because notice we have the same degree in the numerator and denominator. And this basically comes down and touches that 0, 0, and then goes back up and should be symmetrical. So just bear with me on that, but we should have symmetry over the axis. And that's what it looks like. So it has that relative minimum there, that local min, and then it just approaches y equals 1 as a horizontal asymptote. And that's it.